So when we talk about molar volume, it's going to be based on ideal gas law stuff still, okay? But it basically says this: the volume that a gas occupies at a certain pressure and temperature is dependent on the number of molecules in the sample, and I'm going to explain all this to you. The volume of the sample is not dependent on the size of the individual molecules, because most of the gases are large empty spaces between molecules. Then they claim this: 1 mole of H2 is going to occupy the same volume as 1 mole of C3H8 under the same temperature and pressure. And then they give us this little chart here, which, by the way, you have these constants on the back of the periodic table. Okay, so again, you don't need to memorize these or anything like that. That's not really the point. But the point is this, okay? And you can choose to write this down or not. It doesn't really matter to me. But what we have to understand here, okay, again, and this might seem obvious, and you might say, well, duh, but this is a relationship that exists between these variables, right? That's what a formula is. Okay? I mean, if there was no relationship, we wouldn't have a formula, okay? But the pressure is affected by the volume. It's affected by how many moles we have. It's affected by the temperature. R is the only thing that doesn't change here, right? But let's talk a little bit about this. What happens, let's just say, for example, that I increase the temperature of, pick a gas, any gas. What happens if I increase the temperature? What's that? Sure. What happens if I increase the temperature of oxygen? And these are things we probably should know from this unit. But if I increase the temperature of the oxygen in this room, what's going to happen as a result? And you can give me a couple of options here for answers, but what happens as a result? If I increase the temperature in this room, what's going to happen? Yep.
Make the molecules move faster.
Yes. The molecules move faster, right? Step 1, kinetic energy. They gain kinetic energy, right? We know this, I hope. Then what happens? Huh? They move faster. Then what's going to happen? Bigger pressure. Why? Because they're going to be going faster. We're going to have more collisions. We're going to have more pressure, yes? As a result, correct? Okay, and it's the opposite if we decrease the temperature, yes? Okay, so that obviously is going to affect this, right? What happens if I put more moles into this room? What's going to happen? Yeah?
Volume. Will volume be affected?
Well, we're just into this room here, so let's keep it the same. What happens if I put more moles into there? What has to happen? Let's say a pump starts pumping some xenon gas into here. What's going to happen? Somebody, anyone. What's going to happen if I pump some more gas into this room? Pressure is going to go. Why?
Push more into a confined space.
Yeah, there's going to be more. Where do we get pressure from? No. More what? Pressure is a result of? Huh? No. Pressure is a result of what? No. How do you get pressure? You need to know this. This is Unit 2 stuff, guys. Pressure comes from? Collisions, yes? The more collisions you have, the more pressure you have. The more gas you have in this room, the more collisions you're going to have, the more pressure you're going to have, right? So the pressure is going to go up as a result. What happens, just wait before your question here, what happens, let's say, if I don't know, increase the volume? So I decide, let's take the volume of this room, let's go to the gym instead. Let's take all the gas from here and let's go to the gym and put all the gas in that room there. If it was empty before, we'd go to the gym now. We take all the gas with us in this room and go to the gym. What's going to happen to the pressure? It's going to go down, right? Because, of course, now we have a bigger volume. There's going to be less collisions, right? Okay. So we have to understand that there's this relationship between these things here. Now, here's the deal. Here's what molar volume basically is, okay? I'm going to pick a certain temperature and pressure. I'm going to call it STP, okay? Which, oh, by the way, I think this goes back to our quiz for tomorrow, yes? tomorrow on your quiz, I'm going to put some STP stuff and SATP stuff in there. Okay, I know I am. And so make sure you know, hey, I just got to look on the back and find those numbers. And I'm going to make sure that we have some pressure conversions to take care of as well. So, I'm going to start with 62 psi as P1 maybe, and 17 ATM as P2. And you're going to have to make sure that you convert one. Okay? You can convert them both to kPa if you want to. Go ahead. You don't have to. Don't mess it up. Okay? Because you're going to be doing twice the work then. But it's up to you. Okay? So I'm going to pick this relationship at STP here. So I'm not going to go ahead and solve for any variable. Watch this. If I put 101.325 kPa here, because that's what STP is, right? And I'm going to leave this blank for a second. I'm going to leave this blank. I'm going to put 8.314 and 273.15 Kelvin. Okay? Now, I want you to picture a gas. Pick your favorite gas, somebody. Yell it out.
Hydrogen.
American.
No, that's only gas.
Neon. So I'm going to take 1 mole of neon. And by the way, okay, you know this, but 1 mole is equivalent to what? 6.02 times 10 to the 23 neons, yes? Okay, so I'm going to take 6.02 times 10 to the 23 neons. And I'm going to stick them into this. I'm going to use this set of circumstances here. So I'm going to do this test under STP conditions, which I put in there. Okay, and basically, again, because of this relationship that exists, I have to have a certain amount of space to create this pressure. If they're going this fast, right? They have to have a certain amount of space to have enough collisions to make this 101.325, yes? Okay. That number turns out to be this right here, 22.4 liters. Okay? But guess what? Here's the thing, okay? And this is the important part about molar volume. So you can solve for it if you want, but you're going to get 20, I guarantee. You're going to get 22.4, promises. Okay? If you put in 1 mole, 273.15, 8.314, divide by 101.325, you get 22.4, promise. Okay? So this is what's going to happen. But here's the important part about molar volume. Okay? How would this change? How would this question change if I decided, I think Amanda said neon. Who wants a different gas here? No. Hydrogen. What if I use 6.02 times 10 to the 23 molecules of hydrogen? How would this change? It wouldn't, right? Because it doesn't matter what the gas is, right? It's still 6.02 into this space. They still bump into each other just as often, and they still create this pressure, yes? So the point is about this is it doesn't matter what the gas is. You know, you can even pick something bigger if you're like, well, geez, does it work just for the little ones? Guys, what if it was, propane gas that you get from Rob, right? That's the formula of propane, by the way, in case you...
I hear.
Okay. Well, you didn't know how to lay out the cylinder there.
How many colors on group?
I know you're certified, so it's all good. But this is propane, and again, you might say, well, that's a bigger molecule. No, but remember, in the big scheme of things, these are really tiny, and there's a lot of empty space, so it doesn't really matter. If you had 6.02 times 10 to the 23 of these, I would need 22.4 liters of space, basically a water jug, okay? If you think about the big water jugs. 22.4 liters of space. The molecules would be going this fast, and if I had 6.02 times 10 to the 23 of them, it's going to create this pressure, okay? And it doesn't matter what the gas is. That's the point of molar volume, because it's a relationship between the amount of space that you need for that 1 mole of that gas, okay? And it could be any mole of that gas. But that's what a molar volume number is. When you see molar volumes, you're going to see something liters per mole, And basically what it is it's a ratio. It's a ratio. It's a how much space do I need for 1 mole of that gas. Okay, that's what it is. But again, under these conditions, you don't get a choice. It has to be that amount of space because that's the space you need for that gas, right? Now, if we change the conditions, you obviously need a different space, right? So then they talk about SATP. What if I change this to 100 kPa and 298.15? Well, now the molecules are going faster. The pressure is a little bit lower. So it just works out, if I solve here, this would be 24.8 liters under SATP conditions, okay? Any gas in the entire world will occupy that under SATP conditions. You can pick any gas you want in the entire world. If it's at 25 degrees Celsius and 100 kPa, I need 24.8 liters of space to create those conditions for every mole of that gas. And then here's the beauty part about that. What if well, just wait here. So you're going to see this. This was at, let me just write this down here, at STP. Okay, so that's how much space you need. You need 22.4 liters for 1 mole of a gas at STP. I'm getting excited here. Okay. Well, what if you wanted 2 moles of a gas at STP? How much space does it take up now? How much space do you need? Yeah. Yeah, you need twice as much space, right? If you got twice the number of particles, if you don't change the volume by a factor of 2, the pressure is going to go up by a factor of 2, yes? So either you change the volume or you double the pressure. It's that simple. So if I had 2 moles of a gas at STP, it's going to occupy this much space, I guarantee you. Okay? You can put 2 moles in the formula and solve. If you had a half a mole, it's going to be 11.2. Okay, half as much. So that's what molar volume is. It's the amount of space for every 1 mole of a gas. Okay. Now, again, this is under STP and SATP. What if it's not these numbers? Then we have formulas for that. Okay, and that's the backside. So we're going to get to that here right away. You have these. Sorry, I guess I got to write them down here. But you guys have these. Now, this comes from, again, liters, moles. This comes from the ideal gas law. So you're going to see these 2 formulas here. And follow with me here because this is important. You're going to see these 2 formulas here. And again, you'll notice, hey, look, V and N. Oh, that's part of PV equals nRT. Look, RT and P. That's part of PV equals nRT. And all they're doing here is saying, well, how many liters per mole do you have? Look at the units here. Right? This is liters per mole. And by the way, this is called liters per mole. Let's label those, please. Okay? Label them. V is, of course, the volume. Yes. N is the moles. You might say, what's this MV thing here? That's called the molar volume. Okay? And again, all it is it's a ratio. It's a ratio of how much space you need, how much volume for every 1 mole of gas. Liters per 1 mole, liters per mole. Okay? Just like, it's kind of a ratio of mass, molar mass. Grams for every 1 mole, right? Same thing here. Okay? Liters per mole. It's MP, so when you see this is not, again, we can't use big M because big M is molar mass, yes? That's not what this question says. V is volume. That's not this either because we have volume over there. This stands for molar volume, okay? So when the question says what's the molar volume, you're looking at this or that. We'll talk about that in a second. If it says this is how many liters per mole you have, it's this. It's this stuff here, okay? You want to probably use these formulas, all right? This one over here, again, this is, of course, liters per mole. This is the pressure in kPa. This is liters, moles. No, sorry, my bad. Liters, kilopascals, moles, and Kelvin. Don't worry about that too much. And this is in Kelvin, of course, temperature. Okay? And the reason they came up with this formula is because they said, hey, if I cancel out some units, I can still get liters per mole out of this. because kPa is going to cancel with kPa. Kelvin's going to cancel with Kelvin. I'm going to be left with liters per mole. That's how they came up with the formula, basically. Okay. But we have to use the same units as the ideal gas law: liters, moles, Kelvin, etc. Okay. So when do these come in handy? Anytime you want. You can put STP and stuff in here if you want. You can do that. SATP, sure. What if it's not at those two? What if you get some other question, like these ones here? Okay. What if you get a question like this? Well, then you have to decide which formula is going to work best for you. They do the same thing, but of course they involve different pieces of information. Okay. These formulas are on the back of the periodic table. So again, all you have to do is be able to say, hey, okay, let's see this here. It says here, calculate the molar volume. So I'd probably write that down right there. When you see the words molar volume, you'd be like, hey, this is like molar volume. It's on the back of the periodic table. This has a special formula. And then, of course, this is the pressure, and this is the temperature, yes? So if you think about the two formulas that are on the back of the periodic table, which one's the better one to use in this case? V over N or RT over P? RT over P. So you're going to write down the formula. RT over P, yes? You are going to say, okay, I need to calculate the molar volume. So that's what I have. It's already solved for that. So the molar volume should be R T, change it to Kelvin, okay? Just like everything else we do, Kelvin, which I don't know what that is.
309.65.
Good. I'm actually going to look for my calculator here. I think someone's still. Yeah, my drawer. 36 and a half and 273.15. Not that I don't believe you. 309.65. And what's P here? 150, right? So 150 kilopascals. And again, if you do this, you're going to get, help me out here, it's 17? Yeah, no. 17 point what? 16, yeah, you're right. 17.16 or 2 liters per mole. Okay? Liters per mole. The units are a little goofy there because we have to remember, and if you're not sure about that, or if you kind of think about or forget, just write down all the units and cancel out whatever you have there, right? So this is, again, if you want, this is liters, kilopascals, moles, and Kelvin. And Kelvin's going to cancel with Kelvin, kPa is going to cancel with kPa, and you're left with liters per mole. Okay? Yeah? Again, I'll ask you the same question here. Look, under these conditions, it talks about neon, right? What if I changed it to argon? Still be the same, right? It doesn't matter the gas, because the pressure comes from the collision between molecules. It doesn't matter what the molecules are, okay? The molecules doesn't matter. It's irrelevant what they are. Gases are pretty tiny. There's a lot of empty space. It just matters on how many collisions you have. That's where pressure comes from. So I don't care if it's argon or neon or krypton or xenon or whatever. It doesn't matter. Okay? Under this set of conditions, this gas is going to have to, if I have a mole of this gas, I would want to put it into 17.2 liter container to make sure I get that pressure at that temperature. Okay? Again, they're all related to each other. Okay? Now this one's a little different here in that when I first look at this, it says the molar volume. Is that okay for the top part there? I can move it up. The molar volume. So now they're telling me the molar volume of argon is this. Notice it says liters per mole. When I see liters per mole, okay, and if you want to write any of this stuff down, by all means go ahead when you're studying. When I see liters per mole, I automatically think, okay, that's kind of goofy. Liters per mole. That must be an MV equals RTP question or V over N or something like that, because it has to do with something with molar volume, obviously. Liters per mole is goofy, right? What volume will be occupied? This is a mass, and of course I got this argon at SATP. There's a lot of information here, okay? What formula do you think we should use? Again, the key word here is molar volume. So probably something to do with that. And of course, what am I looking for? Volume. So which one do I want to use now? V over N probably would be a better option. Okay. Now, they're telling me the molar volume, so I actually have this, and I'm looking for this. I could probably find that, right? Because I know it's 100 grams. That's a mass. I know the molar mass of argon. So over here, I'd say, oh, I know this. I can find N, because it's this, right? It's 100 grams of argon, which is 39.95 grams per mole. Only one argon, right? AR. And that works out to be, just so you know, it's about 2.50 moles. Okay? And now that I know that, I know N. I know MV, the molar volume. Can I find V? Yeah, cross multiply and solve, or, you know, if you probably would do, most of you guys would probably do this, right? Cancel, cancel. And then I get V equals N times MV. Yes? I like that. Now, to be honest, in this question, they gave you a lot of numbers, but some of them are irrelevant, right? Think about it. What is the molar volume of a gas at SATP? 24.8. Has to be. It's on the back of the periodic table. So they're being a little bit more specific. They're saying it's 24.79. Fine, that's fine. But we already know that gas has to occupy 24.8 liters for every mole. Okay? And then I'd put the 2.5 in here. And I'm not going to round, of course. I'm going to multiply those two numbers there. Okay? And I think it works out to be, if I'm not mistaken, 62.05. And I'd probably stick with 4 significant digits because I have 4. They gave me 4 here, and they gave me 4 there as well. Okay? Is it 62.05? Okay. Okay, yeah.
Oh, so the M and V are together?
Yeah, that stands for molar volume.
Yeah.
Yeah. Yeah, they're not, make sure that they're not separate. That is one variable. Okay? And that's molar volume. But again, okay, we still have to make sure we're using the right units. Okay? Those are still, the relationship only exists with the right units there. Okay? Good?
Yeah.
That's kind of molar volume in a nutshell. But again, okay, tomorrow we have to understand that pressure comes from the number of molecules, right? That's really important. And not tomorrow, I lied. Probably Monday. But on Monday, we're going to talk about the last lesson here. And again, we have to think in terms of how many molecules are going to fit into this space, okay? Based on these conditions. Again, it's all relationships between these things, right? So we just have to think about that. But we'll talk a little bit more about that. And then I'm going to give you some review questions today.